In the previous example problem, we calculated the strength of the Coulomb force on an electron in a helium atom. When we actually plugged numbers in to calculate the strength of that force, we treated every charge as positive. Now we know that isn't really the case. The nucleus of the helium atom contains protons, which have a positive charge, but the electron has a negative charge. So why didn't we write the number negative 1.6 times 10 to the negative 19 for the charge of the electron? Well, the thing is, the negative sign gives us information about the direction of the force. The force will be attractive if the charges have the opposite signs, and the force will be repulsive if the charges have the same sign. In that particular problem, we did not care about the direction of the force. We only asked about the strength of the force. As an example, if you imagine a force of 40 newtons in the x direction, and then imagine a second force of negative 40 newtons in the x direction, that negative sign indicates that the force is actually in the negative x direction. The negative sign indicates the direction of the force, but the strength of those two forces is the same. They're both 40 newtons in magnitude. So for this problem, we have three charges. We have Q1, Q2, 3 with charges as given. Q3 is up here, and we're asked to find the net force on charge number 3. We're told that Q3 is 30 centimeters away from 2, and Q2 is 52 centimeters away from Q1. I could look at this picture, I see a right triangle, and I could use some trigonometry to determine that this distance is going to be 60 centimeters, and this angle is going to be 30 degrees. Now I'm going to look at this picture and ask, what direction do I expect the forces on Q3 to be? I see that Q2 and Q3 are both positive charges. So I expect the force on 3 from 2 to be repulsive. If Q3 is pushed away from Q2, then that implies that the force on Q3 will look something like this, pointing straight up. So this is the force on 3 from 2. I will call it F32. Now there is going to be a force on Q3 from Q1. I see Q1 has a negative charge and Q3 has a positive charge. Because those charges are opposite, the force on 3 from 1 should be attractive. So Q3 will be pulled towards Q1. This will be a different force, something like this, and I'll call this F3 from 1. So what I'm going to do to determine the net force on Q3 is I will have to calculate what the strength of this force is. I will have to calculate what the strength of this force is. I will have to recognize that forces are vectors. I need to add these two force vectors together, find the net force, then find the magnitude of that force. So what is F32? Well, to find F32, I am going to use Coulomb's law. So I could say F32 is going to be equal to Coulomb's constant K times Q3 times Q2 divided by the distance between these two charges squared. So in this case, I would say K, 9 times 10 to the 9. Q3 and Q2, I am only going to worry about the magnitude of these charges. I won't worry about the sign. So we have 65 microcoulomb and 50 microcoulomb. Remember, when you calculate forces and work with other equations involving electric charge, you need to convert to coulomb. So micro means times 10 to the negative 6. So I could write this as 65 times 10 to the negative 6 and 50 times 10 to the negative 6. Then divide by the distance between the two charges squared, which I just erased but was 30 centimeters. So 30 centimeters, we need to convert that to meters. So that would be 0.30 squared. Now I could put these numbers in the calculator. When I do that, I get 330 newtons. So this is the force on charge 3 from charge 2. Next, we will calculate the strength of the force on charge 3 from charge number 1. So I would do the exact same thing. I could say F31 is equal to K times Q3 times Q1 divided by R squared. Now I could say F31 is going to be 9 times 10 to the 9 for Coulomb's constant K. Charge 3 is 65 microcoulombs, 65 times 10 to the negative 6. Charge number 1, 86 microcoulombs. Again, remember, we don't really worry about the positive negative sign for this step. We only care about the magnitude of the force. So I'll write 86 times 10 to the negative 6. And then the distance between these two charges, we use some trigonometry to find it is 60 centimeters. So that would be 0.60 squared. When I put these numbers through a calculator, I find that the force on charge 3 due to charge 1 is 140 newtons. At this point in the problem, we are done with everything that we're going to do with Coulomb's law. The rest of this problem is adding two forces as vectors, which we studied extensively last semester. I look at these two forces and I notice that the force on 3 from 2 is entirely in the y direction. So breaking this force into its components is going to be easy. I could say the force on 3 from 2 in the x direction is going to be 0. The force on 3 from 2 in the y direction is going to be the entire magnitude of that force, 330 newtons. Now I have to break the force on 3 from 1 into its components. I look at the picture that's drawn and I notice that there is a 30-degree angle right here. And there is the rule from geometry that if I have two parallel lines and then a line that intersects these two parallel lines, this angle is going to be the same as that angle. I could imagine drawing a horizontal line on my figure, just like this, and this angle must also be 30 degrees, the same as this angle. We now have enough information to break down the force on 3 from 1 into its components. So I could draw the force on 3 from 1 looking something like this. So here's x and y directions, and then I have the force on 3 from 1, F31. And we know that this angle is going to be negative 30 degrees. Remember, counterclockwise rotations are positive angles, clockwise rotations are negative angles. So I could look at this and say the force on 3 from 1 in the x direction will be 140 cosine negative 30. I put that in a calculator and I get that is going to be 120. I could say the force on 3 from 1 in the y direction will be 140 sine negative 30. And I put that in a calculator and I get negative 70. So now we can add these two forces as vectors to find the net force on charge number 3. So let's see, we have F32x, F32y right there. I could write F31 x equals 120, F31y equals negative 70. If I add the x components together, I get F net x equals 0 plus 120. That will give me 120. I find F net y, 330 plus negative 70, so that gives me 260. Now that we know the components of the net force on particle 3, we could use the information plus the Pythagorean theorem to find the magnitude of the net force on particle 3. So to draw a picture of this, let's say here are the x and y directions, and the net force on particle 3 will be 120 in the horizontal, so here is 120, 260 in the vertical, here is 260, and we are asked to find the magnitude of F net. Here is net force drawn as a vector. I notice a right triangle right over here. So I could Pythagorean theorem this to write F net is equal to square root of 120 squared plus 260 squared. And when I put that in a calculator, I find the net force on particle 3, F net, is going to be 290 newtons. So overall, particle 3 will feel a force of 290 newtons that is pointing up and to the right. To finish our discussion of the Coulomb force, let us imagine that we have a metal sphere that is connected to a ceiling by a thin thread. In this thought experiment, we will assume that this metal sphere has overall zero charge. Now, if we were to take a microscope and zoom in and look at the atoms that make up the metal sphere, we would see positive charges in the nucleus of those atoms and negative charges in the form of the electrons that surround the nucleus. But overall, this sphere is uncharged. Secondly, we're going to assume that the thread connecting the metal sphere to the ceiling is an insulator. So no charge is allowed to travel from the sphere to the ceiling or vice versa. Now we could ask the question, if the metal sphere is just here all by itself, we expect it to hang vertically downward. But how would the metal sphere react if we were to bring in a positive charge from far away and place it somewhat close to the metal sphere? So at this point, pause the video. Think about how you expect the metal sphere to react when I bring in a charge from far away and place it close to that sphere. To understand how a metal sphere will react when a positive charge is placed near it, keep in mind two ideas, the electron C model and Coulomb's law. As a first guess, we might presume that because the metal sphere overall has zero charge, then the metal sphere would not react to placing a positive charge near it. But we're going to see that's not really the case. To see that, remember the idea of the electron C model. In the electron C model, the atoms that make up the metal sphere are ionized. All of the atoms in the metal have lost an electron, and the atoms are largely locked in place in a lattice structure. So all of the atoms have a positive charge. They're pretty much locked in place in my metal sphere. Where did those electrons that all these atoms lose go to? The electrons that all of the atoms lost are just freely flowing between the atoms. They're not really attached to any one atom in particular. So if I place a positive charge near my metal sphere, the positive charge will repel the positively charged ions. The positive charge will attract the electrons in my metal sphere. So let's think about what's going to happen here. Now here is my metal sphere with the positive charge right near it. And we said the ions that have a positive charge are largely locked in place. They're not free to move. So the ions in the metal sphere are just going to remain in place. However, the C electrons are free to move around, and they're going to want to get close to this positive charge. So the C electrons will tend to congregate closer to the charge. And now, as a result of this setup, the left-hand side of this sphere will have a bit more negative charge. The right-hand side of this sphere will have a bit more positive charge. The left-hand side of the sphere will feel a net force towards the positive charge. The right side of the sphere will feel a repulsive force away from the positive charge. Now, if we look at Coulomb's law, the strength of the force depends on the distance between the charged objects. The negative side of the sphere is a little bit closer to this positive charge, so the negative side of the sphere will feel a bit stronger of a force than the positive side. And as a result of this, the presence of this positive charge is going to cause the metal sphere to be attracted towards the positive charge. So this is where I'm going to end this discussion. At the end of this video, think about on your own, how would a metal sphere react to the presence of a negative charge? Do you expect the negative charge to attract the sphere, repel the sphere, or nothing at all? And we could talk about this during the regularly scheduled lecture times.